This video is a continuation of what we found out in the earlier video about the trapez method, where we constructed a formula that told us this thing here, that I am able to approximate the difference between y of tj plus k and y of tj by using this thing here, and then I have an error that has the same order of magnitude as k to the third. Now, if we look at page 16, table 1.3 in the book, it says the truncation error for the trapezoidal method is big O of k to the second. So it has the same order of magnitude as k squared. Now, what is the relation between this term here and this term here? Well, in the book on page 20, where they have just finished finding the trapezoidal method, the difference formula for their trapezoidal method using the trapezoidal rule from integration, they say the error at each time step is big O of k to the third. So that's also what we say. And then they say the resulting error is therefore m, which is the number of time steps, multiplied by something that has the same order of magnitude as k to the third, which is to say that the resulting error is t divided by k multiplied by something that's big O of k to the third, and so it is big O of k to the second. And consequently, the truncation error is tau j and has the same order of magnitude as k squared. Now, to be honest, I find this approach a bit hard to follow, because who says that we can just multiply our error linearly with the number of time steps? That's not a given. That's not very clear at all. So in this video, I think we should just talk a little bit about the notation that there is in the book and what we actually mean by truncation error. And the thing that I will take up here is, by truncation error, and I would like to use the term local truncation error, we mean the truncation term that is removed from the differentiation formula. With a big fat line or differentiation formula when we construct the finite difference formula. So when we talk about, for example, truncation error in the trapezoidal method, then this term over here is not the truncation error nor the truncation term in the differentiation formula. And why is that the case? Well, that is because we have not isolated the derivative of y in our formula, and we need to do that before we can locate what the truncation term is. So the differentiation formula for the trapez method is, well, let's see. I have y of tj plus k minus y of tj, and then minus something that has the same order of magnitude as k to the third, and I divide all of that by k halves, so I multiply by 2 up here, and then I also minus y prime of tj plus k. So this is my differentiation formula for y prime of tj. And what I see here is that I have a lot of stuff going on, but in particular, I have the term big O of k to the third divided by k, which has the same order of magnitude as k squared. So this is equal to y of tj plus k minus y of tj, then multiplied by 2, and minus y prime of tj plus k, plus this thing here, a truncation term that is big O of k squared. And that is where the truncation error comes from. Now, maybe in some way we can explain that this construct warrants the multiplying by m construct we have up here. I will neither critique the book nor try to explain something that I can't understand. But anyways, this is then what is the truncation error. This is the truncation error for the trapezoidal method. So whenever we talk about a truncation term or a local truncation error, then always find it by first isolating the derivative in question and then locating the term that we remove in order to construct our finite difference formula. Okay. So that was a little bit about truncation error, and you have probably already seen here that the book just uses a lot of different words for error. The book uses the word truncation error. It also just says error at each time step or a resulting error, and that might be confusing. And that is also why when you do your reports and when you plot something that has something to do with error, just make sure that you always explain properly. Is it the truncation error? Is it the error at each time point? Is it the error that is given by the difference between the exact solution at the endpoint of the interval and the approximate solution at the endpoint of the interval? Or is it the max error that is given by the maximum of the deviations between the approximate solutions and between the approximate solutions and the exact solutions? So always remember that the term error is not as simple as you might think.